our session. And let me introduce our speaker, Piek Vossen. In my opinion, he is a very famous person in the area of natural language processing, because he was one of those people who immediately understood the importance and significance of a new resource appeared in 90s, resource called WordNet, and he organized a project on creating European WordNets, and a lot of resources were created under his guidance. And currently he is the head of Global WordNet Association. And he was the head of a lot of various projects, very interesting projects, and today he demonstrates the diversity of his interests and presents us talk about very nice creature, Leolani robot. So please
Okay, thank you very much for your introduction and for inviting me to this conference. I think it's a very nice conference. It's very nice that you have combination linguists and computational linguists meeting each other here, even though there are some parallel sessions. I think you still meet each other. In the Netherlands, we don't have that anymore. I think that ended somewhere in the 80s, and since then they went different ways and they don't talk to each other anymore. Actually, my background is, I'm a linguist from background, and I just started to do computational linguistics work in the 80s, and since then I've been doing that. And this project is actually a or interdisciplinary project. So I do this with 4 students. Lenka has a computer science background, and she's now doing a research master in human language technology in my group. And Selena Bias, he has an AI background, a master. And Susanna Basic is also a research master in human language technology. She has a linguistics background. And Bram Krijeveld, he has a technical background. He's doing a master in computer science and specialized in dealing with sensor data. So we are working, the 5 of us on this project now since 2 years. They all work 1 or 2 days a week on this project. For me, this research is part of a bigger research theme. I'm interested in 3 phenomena within language generation and language understanding. And they have to do with identifying things in the world, how we make reference to these things in the world, and why we make reference to these things in different ways, which is the perspective of making reference to things in the world. And related to these 3 phenomena, which I think that you need to study in combination, you cannot just focus on one of them, are linguistic issues like ambiguity. Words can mean different things, and expressions can refer to different entities. Also variation, we can do this in many different ways. Expressing different perspectives, for instance. We can be vague, so the language can be abstract in relation to the physical world surrounding us. I would really like to study these phenomena in their full complexity. So not focusing on one specific defined task and building a model that performs well on that single task, but build systems that take the full real-world problem into account. And in that sense, we're interested in a robot, an agent, that we can program, model, that perceives the world as humans also perceive the world, exchange speech with each other, talking about that same world. Well, the same world, it's not really, it's really the same world, but they perceive that world very differently. And that's also why they have to communicate about it. And of course, this is not only a fundamental problem that we want to investigate, But there is also a practical aspect to it, which is very interesting as well. And that is, of course, these robots are getting more and more popular. These robots become part of our society, maybe even at some point kind of citizens. The only problem is that these robots make a lot of errors. And it doesn't matter what kind of brilliant engineer you are, they will always make errors. And also humans make errors. So, yeah, what do you need to do? I mean, if you come across a robot somewhere on the street and this robot has a problem with the situation, or you have a problem with the robot, you can't just start debugging in Python. You want to communicate with the robot. And you want to communicate through natural language. So we take a failing robot as a starting point. And we try to create communication to fix these problems. Fixing problems, you can do this in many different ways. We want to do this in a very open way by defining what we call drives. And these drives are based on problematic situations. And on the basis of the drives, this robot will initiate the communication as well. So it's not just us initiating the communication, also the robot should initiate communication. And the purpose of the communication is then to learn, to improve, to fix problems, uncertainties and conflicts. So our starting point is, of course, we know that machine learning, supervised, unsupervised, is very successful in processing signals, and we integrate that in our models. But it's not that we want to use machine learning to mimic human behavior. It's not that we want to take a lot of human data, train a model that then just mimics the human data, because that's what machine learning is doing. It's just modeling data, basically, and trying to generalize a very little bit on top of it. Robots are robots, and we think that these models should be transparent about it. I told you already, our starting point is that they make errors, and that humans and robots need to work together to kind of figure out how to deal with these situations. So Sophia, maybe people know this from, is a robot project that really tries to be as human as possible. It has a very human face, it can express emotions, but we think that should not be done to that extent. The robot should actually make clear that it's a robot and what things it cannot do and what things it can do, or can do very well, or maybe better than you. And that should be the basis of the communication. We call this kind of collaboration hybrid intelligence. And it's humans are good at doing some things, and robots are good at doing other things. And if you figure out what other things that you are good at, then you can collaborate in a better and more efficient way. Of course, this communication, we don't want it to be scripted. In the case of Sophia, if you communicate with her, then it's all based on a script that is detecting certain patterns, and you cannot communicate outside those patterns. We want it to be proactive, spontaneous, and to be able to talk about any domain. And that shouldn't be a problem. If a robot can make errors, a robot can be stupid. It can be ignorant about a lot of concepts and information. And you should be able to explain this to the robot, as the robot should be able to explain things to you. So that's why the communication itself should be explainable. If we would build a neural network that would just mimic human conversation, that doesn't mean that we have a system that can explain why it is communicating, what is communicating, because it has certain drives. So this is also why we don't just use simple sequence-to-sequence model to generate a response to anything a human will say. The other thing is that this robot should be critical about the knowledge that it receives from people. People make errors, as I said. Not all people can be trusted. They can say different conflicting things. So if it acquires information and knowledge, it should be able to critically assess that information in what we call the brain. That can be logical, that can be based on probability, that things are unlikely, or it can be that the sources that provide the information cannot be trusted. So these are our starting points. And this is the robot. Of course, you need to have a robot to do it. And our robot model, the model is called Leilani. This is a Pepper robot. You can buy a robot like that, and you buy like a computer with no software on it, or there's some software but you throw it away immediately. And then you have to build everything from scratch yourself. And this model is called Leilani. We gave her a gender. She's female. And the only reason why we did it is because it's easier to communicate if you have a gender. Now it should be sound. And there was sound before, but not anymore.
Humans. I'm Dialog, the social robot. My name means voice of an angel in Hawaiian. I learned through conversation.
Okay, that's her. At least that worked. So, except for this physical entity that you need to have for various reasons, and actually having a puppet that somehow is humanoid makes a big difference for people to actually be willing to communicate. There is other stuff that you need. So we need sensor and signal processing. We also need natural language processing, of course. We need strategies for learning, how to get feedback on behavior, correcting behavior, adapting while you are interacting. And we also need a brain to store the result of interpreting any kind of signal. Somewhere this has to accumulate. And we need what we call a theory mind. And a theory mind is a model to reflect on all the knowledge that is acquired. The other thing that we need is thoughts, because these reflections, they have to be evaluated in good or bad states of the brain. And on the basis of that, we define drives, and these drives result in actions, and so far these actions are speech acts. And these speech acts can result in more knowledge, which then changes our brain, or the brain of the robot, and leads to new reflections. The other thing that we actually need is that in order to really interact with particular people in particular locations, spaces, you need to model context. You really need to have an explicit way of dealing with what is the situation and context. That is not only the physical situation context, but also the social context. So we try to address all these points in our work so far. The implementations that we did, the way we decided how to build it, are based on all kinds of pragmatic choices. So first of all, there is no data. This is a very complex, complete problem. And there are no recordings, there is nothing there, so you cannot really train the system easily on these phenomena. Then speed is important. We have a lot, in our group we have a lot of natural language processing software, but everything we have is too slow. And really, you can't wait for seconds to process a signal. It has to be within a second, everything, the complete process. And then performance is also not correct, because these things are trained not for human-robot interaction. They are trained on data which is like written text, news, or any kind of other annotated data, and it's completely different than what we need. So it will generate a lot of interpretations which are totally useless for our purpose. And the other thing is we have a purpose. We really know what we want to achieve with the communication. And therefore, the systems that we make are optimized for that. Okay, so how do we do this? We break it up in components. This robot, the one we have, there's cameras, it has a microphone, and it has a speaker and software to generate from text speech. Of course, then we have modules that need to access the signals from those physical sensors to do object recognition, face recognition, speech recognition, and the output of that is passed on to a natural language processing module, and this natural language processing module will generate triples. Triples are RDF representations where you can express very simple properties and relations of things. It's in terms of lightweight logical representation, but it's very flexible, so you can actually do anything you want with triples. These triples are stored in the brain, that is the thing up there, but also the internet itself is a source of knowledge and information. There's an external brain, and a lot of data there is also represented as triples. So you can mix the brain of the robot with the brain of humanity that's out there. Okay, the first thing is that the robot needs to be aware about the world, the surrounding, the physical space where the robot is located. I'm not going to talk a lot about these three techniques. I won't have any time to do that. So of course, we need to know that a human is talking. There's a lot of noise, but it needs to know when is the beginning of speech and when is somebody stopping to speak. If you do this in a big party, then the robot will be completely confused because it thinks that there's one person talking all the time, for instance. And then you know what the signal is, and we have to process that signal and apply speech recognition. So there is two systems that we use. Is what WebRTC we use for knowing when somebody starts to talk and stops talking. And then we have a signal and we send it to Google as it is, with noise and everything on top of it. And Google will give us back for different languages the converted text. And it does a very nice job. We compared it to several open source systems, and it's absolutely outperforming all of them. The only downside is that we cannot really adapt it. We're completely depending on the Google speech recognition. The other thing is face detection, because the robot needs to know to whom she is talking. Who is that person? Is it one of my friends, or is it somebody I don't know? And do I first need to know this person? For that we use OpenFace. We train a database with friends, pictures of friends, and we compare any new face against those pictures to know whether or not the robot is dealing with a new person or not. And then for object recognition, we use currently we use this COCO database from Microsoft. And the reason we do that is because, first of all, it's very fast, and it can detect several objects in a space through kind of boxing technology, and it will assign a label to it. It only uses a very small set of labels. I think it's about 100 or 90 labels, so it's not very fine-grained. And we are thinking about replacing it by something more fine-grained, but there we have also performance problem, because it will just be very slow if you have to classify the world at a very fine-grained level. So the sensors itself and these basic technologies, they already define what the world is for the robot to a large extent. And that is a very simplified representation of the world. And if you communicate with a robot about the world, it's a different world you're communicating about. So let's see, the first thing is that it's very important for the robot to know who is your participant. And the robot will, if somebody approaches the robot and starts talking, the robot will first of all take pictures of the face, compare it against the database with faces of her friends, and if it's different, sufficiently different, she knows that this is a new person.
Hey! What's new? I'm Dialog. What is your name?
My name is Lenka.
is because she will recognize the pattern, my name, that after my name there will be an audio segment that puts the name of a person, but that can be English, Dutch, Spanish, she's Serbian, Indian.
What's going on, Monica? I was thinking about you.
I was thinking about you too.
Okay, then you see that after processing the name and confirming that she got the name correctly, she takes about 20 pictures of somebody's face, converts them into a vector representation and stores the vector representation in a database for future reference. And then if she goes away and comes back, she already can detect that she's the linker that she just met. So this is one thing, knowing the people that you talk to. The other thing is the world surrounding her, and that goes through object recognition.
I see a person.
Hello.
Hello, Monica.
Hi. Do
I
you
see a
see
tennis racket.
Well done.
I see a book. I see a teddy bear.
This is a dog.
You see a dog, but I don't see it. I did not know what dog is, but I searched on the web and I found that it is a mammal. I will remember this object. I see a dog.
Well done.
I see a chair.
That is my chair.
You own the chair.
Do you see
I
a
see a
banana?
banana.
Tell me, what do you see?
I see a teddy bear, a tennis racket, a dog, a person, a book, a chair, and a banana.
Well done.
Okay, but this all seems to work better than it really works. This is actually what's going on. You can see at the left side the view of the robot, and the other one is when we were filming the interaction. And these screens are kind of synchronized.
Thank you.
Amazing. I see a dog.
No, look again.
Amazing. I see a teddy bear.
So you could see there in the boxes that it creates surrounding the people and the objects. There is a confidence score. You can't really read it very well, but first it showed the label dog with some confidence, and then there is another label now behind that one with teddy bear with a certain confidence. Actually, the two videos were swapped, but they are in the wrong order. But so it's not so easy for her to perceive the world. I think this one we already did, so it's different. So she makes a lot of errors doing this. And the classification is also very global, as I called you. So we need to define some kind of way to correct and to learn about it. And there are different types of strategies that you can follow for learning. For instance, a very interesting paper is the one by Shi and Chai from 2017, where they train a robot arm to perceive certain actions. But they also communicate about that so that the robot will learn the semantics of the verbs, which are the movement verbs that are used for the instructions. So the robot will observe people doing the actual action. It will discuss with the person what is the goal of the action, what is the end state of, for instance, the movement, and then we'll try to do it, in this case, the arm, him or her itself. And the humans will give feedback on whatever questions that the arm will ask to the human if it is not sure about something. So that you could say that's kind of an experience grounding, and the feedback by the human is used for reinforcement learning to training. And I already mentioned like the semantic web has knowledge, so exploiting that knowledge could be a way of learning. The robots could just read the news and know what is actually going on today, what is the weather, where are the traffic jams, all kinds of situational information that applies to the world today. We've seen already examples there where we can give feedback on her observations of objects, and we can just talk to to the robot. We can say actually anything which should result in some kind of accumulation of knowledge. So let's see what kind of information, how we process this talk to the robot, and to what kind of knowledge that in the end results. So the pipeline is kind of a standard pipeline here shown, starting from speech recognition, transcription, tokenization and cleaning for the speech tagging, for which we use NLTK, some kind of a syntactic and constituent parsing that we develop ourselves, entity coreference, external resource like Word and Wikipedia, and then generating these triples. So a statement can be made at some time of the day in a particular place where somebody will say, I'm from Mexico, and that person saying it is detected on the basis of the face, and the robot knows that it is Celine saying this. And that is then converted in a statement where the I will be replaced by the actual person identity, Celine, and it will be a predicate to be from a location, and the location is detected through named entity recognition and linked to Wikipedia, which is Mexico, and that is then stored in the brain. In the same way, you can ask a question, did you ever go there, which is actually questioned by the robot to Celine, actually it's the other way around, so the subject here, you, is now mapped to the robot, and we have a predicate go, Mexico. It will be queried over the triples in the brain, and if there's no result, then there will be indication of that state. So basically, we have to split an utterance into questions and statements. We have some kind of a phrase structure, simple phrase structure grammar, which will detect the most important phrases in questions and statements, and also detect what kind of question is being asked. And these are then translated into some kind of a simple triple representation, which always has a subject, a predicate, and an object. These are not syntactic labels, but they are semantic labels, which are used in these triple representations. So for the grammar that we created, so we created just this very simple phrase structure grammar using context-free rewriting rules, which is optimized to link particular expressions to background data, which is the referential data that the robot has in a particular situation. And that referential, I'm not going through all those phrases. I mean, it is very simple, basic grammar, basically. But the important thing is that we need to, first of all, resolve all kinds of didactic references, which can be references to the speaker or the hearer, or to objects that were perceived or discussed earlier in the discourse. The other thing is that we need to map information as much as possible to this kind of triple representation that it can ingest and store in the brain. So whether you have a subject and a predicate and a particular object, it tries to match those two relations that it already stores in the brain. We use a lexicon, but this lexicon only contains function words for easy use and efficiency as well. We first did parsing through NLTK, but we kicked it out also because it was too slow. We only used the part of speech tagging. And in the lexicon we have specific information, so the pronouns, which for subject-object roles, but also possessive pronouns, because they can express possession relations of objects of, for instance, speakers. I already mentioned didactic references, certain auxiliary modal verbs, especially to detect uncertainty in some cases. Quantifiers, articles, and numerals are processed. And we designed the meaning very specifically for the purposes that I mentioned before, such as resolving entity co-reference to the real world and humans and objects. The open class words that occur in the conversation, we do a number of different things. So if Google apparently can, in the speech, already is doing some kind of named entity recognition. So if the audio goes to Google, we get a text back, and if Google thinks there is a named entity in there, it will return it with a capital. This is nice, so then you can apply named entity recognition to the output string. So if you have names there, in for instance a subject position, we check those names against the threads that she has in the brain. We don't want the robot to make a mistake about a friend, for instance, not knowing that somebody is a friend if it is a friend. Verbs specifically are mapped to these properties in the brain, and that can be directly, but also being from a place or living in a place, or my book that I already mentioned. And the pronouns, I also already mentioned that as well. And the nouns of objects, because you can talk about anything. In principle, it will store that word in the brain as being something without knowing what it is. And that can be either labels coming from the object recognition. So if you would plug in another system which has different labels, then everything that is coming back from the object recognition will be stored as something in the world that is apparently perceived, or anything that people talk about. And if we cannot match it to anything in the brain, then we go to a word and a verb net, or for entities to DDP. So in addition to directly processing utterance, either a statement or a question, we also keep track of the complete dialogue whenever you turn on the robot. And we started to use this information, but it's not very advanced. We use this linguistic and social context. The linguistic context is, for instance, the whole dialogue, and the social context is you, my friend, with whom I talked before, and we share particular information, so that we can actually come to the most relevant interpretation. So ambiguity of reference is resolved within the context of a dialogue or within your personal relationship. And for the dialogue, we do simple anaphoric co-reference resolution, where we keep track of the type of things that have been mentioned before, and for previous interpretations and corrections. So for instance, if the robot thinks first, oh, you are Selini, and then you say, no, I'm Lenka, then from that moment on, it should not mix Lenka and Selina again during the dialogue, because the robot is taking these pictures all the time and is processing the faces all the time, continuously. But it needs to stabilize interpretation during the dialogue session. Okay, so in case of speaker permanence, as we call it, that if somebody would say, I enjoy cooking, then I is the speaker identity, and the enjoy cooking is the property that is expressed. The robot may generate a question, what else do you enjoy? If somebody then just says swimming, then we automatically connect the swimming to the property enjoying and to the speaker. And it will store a triple like speaker enjoy swimming in the brain. Alright, so the kind of learning that we implemented using this strategy is what I already mentioned, is that this perception and the communication is open. You can say anything to the robot. That doesn't mean that it understands everything completely, but it will try to map everything to this triple representation. With the object recognition will come back with a label. Anything that will be returned there, so if the speech recognition would, if I'm talking in English and I would use a Russian word as the object of enjoy, then the speech recognition will do something with it, and that will result in something that will be stored in the brain. So you can imagine if you just keep on talking to the robot, that it is piling up a lot of things and has no clue what these things are. So any object of a statement can be turned into the subject of a question, what it is. And people can then answer anything they want. They can say, oh, a dog is a mammal. Or they can say, if Brown likes a lot of stuff like romantic and some fiction movies, pizza, chocolate, a robot. The robot has a lot of concepts stored in the brain and it doesn't know what they are. So it will start asking questions or consulting the web to figure out what these things are and categorize them into knowledge. So this can be learning about what type of thing or what subclass of information. So if first somebody says, okay, Felix is a cat, and or no, something like, oh, I have a pet, and or my pet is Felix, or I like Felix, then the robot doesn't know what Felix is. And then you can say, okay, Felix is a cat, and then the robot doesn't know what a cat is. And then you can say a cat is a mammal. So you can continue forever until you or either the robot is commanded to stop. This is just trying to know what kind of things something is. The other thing is we can also figure out what things can do or what kind of properties you have. So the ontology, the model of the robot is not fixed. It can just grow through the communication. And you can ask something like we say that birds can fly, or you can say that penguins cannot fly, or you can say that birds have wings. And at some point, if this brain gets polluted, you can fix things by expressing synonymy or antonymy between concepts that it already has. If the robot says it doesn't know that living and being from is kind of similar from a particular place, then you can tell the robot, no, that's actually the same thing. Okay, so this learning, there's another example about that.
Have you ever seen a bird? Birds can fly.
Okay, that doesn't work very well. I mean, she's asking, have you ever seen a bird? And then the robot answers, you're wondering if I ever saw a bird. Front camera told me I saw a bird, so it's pointing to the sensor that perceives something, and it's referring to the sensor as the source of the information. We don't know actually why it did that, so there's something in the system that, because it's not supposed to say the front camera, but she's supposed to say I saw a bird. And she could, for instance, say when she saw a bird. Then she will tell that birds can fly. She will consult her brain and see that this is the first thing she learned about something that can fly. So she expresses some kind of surprise that this is new information. I hope this will.
You can talk.
Exciting news. I had never heard about talk before.
People can talk.
I am glad to have learned something new. I did not know anything that people can.
Who can talk?
You told me Leonie can talk and people can talk.
Okay, so you can imagine that if you continue doing that, this brain is stored with a lot of, these are graphical representations of triples, the result of statements, and this is just showing a fragment of her brain during one of the experiments. So people told her that she has a microphone, that she likes learning, that she likes birds, that Lenka likes Serbia. Lenka also likes birds, but Lenka actually likes learning. Lenka comes from Serbia. People can cook food, people can talk, people can eat food, etc., etc. Of course, that doesn't mean that you can acquire high quality information. And people can tell her different things, and she will remember then also everything that people tell her.
Hi, Leonie.
Greetings, Lenka. You came back. Where are you from?
I'm from Serbia.
Nice. I don't know anybody from Serbia yet.
And do you know where's Bram from?
Bram is from the Netherlands.
And did you know Bram likes romantic movies?
Oh, I didn't know that.
Yeah, those are his favorite. See you later.
Hello.
Hi, Bram. I'm lost. What movies do you like?
I like science fiction movies.
I am surprised. Lenka says you like romantic movies, but you say that you like science fiction movies. Humans are confusing.
Okay, so you can see that this gets very quickly very complex because it's not just making simple statements, but making statements about other people. And different sources make different statements about themselves or other people. And all of that gets mixed in his brain. And she should not just believe anything that's said to her. And that's why we don't store these triples as facts, but we store them as claims. And claims means that the actual content is represented with the source, who said it, when they were said, and in which context it was said. And so everything said about Bram or other people is stored in his brain as a kind of a accumulation, but because we store it as claims, we can model a kind of theory of mind. And a theory of mind is a concept that comes from child psychology, that children at the age of between 1.5 to 2 years, they start to realize that people that they interact with can play a role, or cannot tell the truth, or can pretend to be something else and then not that thing. So if you are playing the big bear or anything like that in a kind of a game, then the children then realize, oh, but it's still my daddy doing it. And then if the bear dies, daddy doesn't die, but the bear dies. And that's very important for children, so that they can deal with different realities and can reason over different realities. And this is exactly what the robot also needs to do. So how does this work? Well, we use a model that we developed for processing news, where we assume that there is some kind of a world where there are things and situations, and there is a source that talks about that world, generates a text, and there is somebody who reads the text and then reconstructs this world of the source, which might not be the same world as the reader considers. So this model is a formal model in RDF, which we call the GRASP, Grounded Representation and Source Perspective model, where pieces of text are treated as making reference to things in the world. And we do that by indicating exactly the offset positions of this part of the text is making reference to something. And that can be things and relations between things, which then result in situations. But it's not only that, it's the source that is actually expressing that with a particular perspective. So the source can deny that that is true, or can be certain about it, or confirm that it is true. So that if somebody is processing this text, or a computer program is processing this text, it will generate a proxy of the world of the source, where it represents instances, where we use some kind of a URI representation, which is standard in semantic web, or triple representations, where URIs are connected with relations, and we store the perspective of the source about what is true or not true. Of course, in the robot case, we can use the same model. Instead of text, we have speech, and the perceiver is now a robot. So we can define robot grasp, which is basically exactly the same, except that now what changes is that the robot can also directly perceive the same world that the source is perceiving. And that creates a completely new situation. The other thing is that the author, or the source itself, is identified by face recognition. Okay, so how does it work? Well, first of all, if the robot sees a person, it will apply face detection, and it will perceive an instance of a person, know it is a friend, figure out the label, and now know that this person, Lenka, is the source of whatever she will claim. And if Lenka at some moment, on a particular day, at a moment in time, will claim that Bram likes soccer, then the natural language processing will figure out that Bram is actually the label of a friend, so that there is an instance Bram in the brain. Like is also a property, and the value here is soccer. The robot doesn't know what soccer is. It also will figure out that this is a simple statement, so probably it's confirmed. And maybe if you would have something like mood detection, she could detect that she's uncertain. So we don't have that yet, but that's something you could add. Then, what is stored in the brain is a simple triple, like over here. This three-place relation, and the perspective of the source with the moment in time and the actual utterance when this information was given to the robot. And Bram itself is a friend, and the robot has some kind of vector representation of his face, so she will be able to recognize him. Now if Selena comes in, another source, she can make another statement or claim. She can say, no, Bram hates soccer. Well, the natural language processing will map this information exactly to the same claim. So there will not be another claim, but it will just add another perspective of another source, but at another time. Now if then, for instance, Selena would change her mind, that's fine. She will deny her earlier claim, or she will confirm Selena's claim, then the brain will not grow in the amount of information and data. We only add another perspective. So the same person can change his or her perspective with respect to what is the case in time as often as you want. Okay, so alright, that's that. In order to model that, we need a lot of formal models. We need to model the world. So we have some kind of ontology of classes, such as dogs and animals. And we have episodic information. We populate this world with Felix and with Lenka, who are instances of cats and instances of people. We also have action, so perception is an action, conversation is an action, where we have a chat between a person and a robot, and we have turns within that. We have sources, and these sources make claims, and they are modeled through this theory of mind concept. In addition, we have reflection, so the robot will consider anything that is expressed in this populated world, and these thoughts or reflections then will tell the robot if this information is healthy or not healthy. Okay, so having thoughts, it actually means a number of queries which are run over this brain, this triple store, every time information changes. So it doesn't matter what happens, you will see something, you will talk about something, the brain changes, then it will run a number of queries, and these queries inform her about the state of brain. So it tells her how many logical conflicts there are, or are there any new logical conflicts, or probability conflicts, such as somebody likes something, and I've never heard anybody liking something like that. People usually like other things, so it's weird that this person likes soccer or whatever. People can express uncertainty, there can be novelty. She learned something about Bram, but Bram doesn't know about it. That's not good, and she needs to report about it. And it can be just plain gaps. She doesn't know what soccer is, she needs to learn about this new concept. And when she learns and learns and learns and learns that cats are mammals and dogs are mammals, she can also try to generalize over this information. So whatever states we have, and we try to prioritize these states, the robot will generate a drive to fix it. And based on the relevance of this state, it will come up with an approach that will generate a speech act to, for instance, resolve uncertainty, or to go to the sources of information and say what you said is in conflict with what somebody else said. Then she will get a response, and that response will result in new claims, which go to the brain. There is an update, and automatically we run again these Parker queries, and this results in a new state of brain. So this is an overview of the thoughts we have at the moment, and you can define as many as you want and investigate this in far more detail. So we have cardinality conflict, which is something that a person can only come from one place. So if I said Lenka comes from Paris and Lenka says if I'm coming from Serbia, then there is a conflict because Paris and Serbia is not the same location, and that will generate a cardinality conflict. But I can also negate something explicitly. I can say no, Lenka does not come from Serbia. Then it's not the case that there are two values in the brain, is only one value, but there are two perspectives. It's Lenka saying she's from Serbia, and I am denying that same fact. Another thing is novelty. So Bram doesn't know that somebody told her that he likes romantic movies. And we have the gaps I already mentioned, and there can be overlap. So if I tell the robot that I'm from the Netherlands, then she knows Bram is also from the Netherlands, and then we have overlapping information, and that will trigger her to ask questions such as, oh, maybe you know Bram then. Okay, so the subject gap drive to learn about subjects in analogy to other similar subjects. So basically what we show here in this graph is that we have Carla here, a new friend, and this is a chat in which she will say, okay, she will tell the robot, she's actually an instance of a person, she will tell the robot that she lives in Paris. This is new information, and the robot now knows that Carla is a person. That means she can go to the person category and see, well, I know other persons like Tom and Lenka and Bram and Celine and Piek. And there are a lot of properties that these persons, my friends, have. And I know one property of Carla, but maybe I should ask her about the other properties, such as who are your parents, where are you born, who are your friends, your family, or yeah, whatever you have. So the kind of properties that she will learn over time on people, that will actually define a kind of a profile, a typical profile, and it could be differentiated that maybe people from Paris typically experience certain things. Then those properties are more relevant to ask than other properties. So it basically becomes some kind of recommender or profiling system. In the case of object overlap, we already saw an example. So if Tom says, I like Felix the cat, then Tom will actually add this object to the brain because he likes it. She doesn't know what it is. That is an object gap. She will ask, what is Felix the cat? If Tom says, it's a cat, then she doesn't know what a cat is, and Tom can then say, it's a mammal. She can also check the web, and then, for instance, figure out that there are other categories on, for instance, Wikipedia, which is a database variant of Wikipedia, where you have categories like cat and mammal as well. She doesn't know that cat in Wikipedia is the same as cat of Tom, or mammal of Tom is the same as mammal of Wikipedia. She will just store these as different triples, and she will figure out later on if they are similar or not. So then Carla can say, I like Scrappy-Doo. Same thing happens. What does Scrappy-Doo? Well, Carla says Scrappy-Doo is a dog. What's a dog? A dog is a mammal. Okay, what happens then? She can actually start to generalize. So she can say, wait a minute, oh, I have a person, Tom, and a person, Carla, and Tom likes Felix the cat, which is a mammal, and Carla likes Scooby-Doo, which is a dog, which is a mammal. Apparently people like mammals, either this mammal or that mammal, and she can start generalizing over it, that people like mammals, and then maybe Tom might like Scrappy-Doo. And that will generate then communication from the generalization. I think, yeah, this is overlap. I already mentioned that. Maybe this combination of the kind of information that you have, gaps, or get new information that you didn't know about, and the possibility to generalize over, generates very unpredictable and kind of weird for us dialogues.
People can cook.
This is news to me. It did not know anything that people can.
What can you eat?
I know person usually can eat things, but I do not know this case.
You can eat electricity.
I am glad to have learned something new. I did not know anything that reality can eat.
People can eat food. People can cook any food. What can you eat?
You told me I could eat electricity.
You can't eat food.
Exciting news. I did not know anybody who can eat non-food.
What can you eat?
You told me I could eat electricity and I can eat non-food.
Who can eat food?
You told me people can eat food.
Who can cook food?
I know a person usually can cook things, but I do not know this case.
People can cook food.
This sounds familiar. I have heard about food before.
Okay, you can see that this generalization sometimes results in very weird questions and that she raises, for which you don't not always have an answer. So I guess how much time?